Okay, we'll make a start now. So there would be a test tomorrow. I'll talk about the test a little bit later and few other points that have cropped up. So I'll talk about those once I finish this part of the presentation and then go on to discuss the test as well as some of the issues that some of you have emailed me. So we have looked at reaction, force and equilibrium in the first couple of weeks, and then the last 2 weeks we looked at trusses and how to solve those. And today we are going to embark on our next topic, which is shear force and bending moment diagrams. Now, what are those? So in terms of where we are, so you have got forces, reaction, trusses, and then this is the last one from the first lot. First lot, by which I mean how big are the forces, for example. So this is bending plus shear, and then in the next half we'll be looking at the resistance of the structures. So if you remember, the E is the effect of the load that has to be less than the resistance of the structure. So we are still in the first bit, and this topic would be the last along the first bit of the topics. So, and then we'll go on to the next one, the material behavior quickly, stresses in the beams, beam deflections, and few other stuff. So, what are the beams? Beams are normally carry loads in bending. So one of the ways they do carry load is by bending in a way, so which is very different than pull and push type of forces that trusses use. So trusses use forces in the directions of the length. So either a truss member can be extended or pulled, or it can be compressed or pushed, for example. So the load acts perpendicular to the cross section in a truss member. Beam, on the other hand, they bend. So, and they resist the load by bending. Now, we normally refer to the beam, draw a beam without drawing that cross-sectional dimension, just do it as a line. And the rationale behind that is that the effect of the load that the beam is carrying does not vary in the other direction. It only varies along the length. Beams are very common, starting from a bridge to these buildings to span the wing of an aircraft, for example, blades of the helicopter, for example, or the solar panel, for example, in the space stations. So it is a bit tricky to analyze this than the bars and trusses, but we need to know these two quantities. You probably haven't heard them before in this context. Of course, you know what bending moment is, but in this context, we will be talking about bending moments means the internal forces in the beam and the shear forces. So if you remember, we calculated the member forces in trusses by making a cut, and then used Newton's third laws of motion, saying that if it is in the equilibrium, then there must be forces from the other side that would be giving it to into equilibrium. And then we found indirectly what would have been the force inside the member. So exactly the same type of approach that we will be doing now. So you will cut a piece of a beam and see what sort of force will make it under equilibrium or keep it under equilibrium. So imagine you have got a beam like this. So just a beam supported at two ends and loaded by a series of uniformly distributed load. Now, if you make a virtual cut here, with a piece of scissors, pair of scissors, and then look at only one part of it, then of course then you are looking at this won't be under equilibrium, because these forces WL/2 minus this little bit of load must be, now this bit of load is missing from there, so let me. So there would be this load that would be acting there. So this load would be acting there in a way. So this is WL/2 is higher than this bit of the load, because if the length is say less than L/2, so that means there will be net forces acting into it. So if you do the summation of vertical equilibrium, definitely the part of the beam towards the right hand side must be providing a resistance force to this beam going downwards, so that this internal force, so this is an internal force, so this is internal force, and where it is coming from? It is coming from the right hand side of the beam. So this part of the beam is giving this, so it is coming from the right hand side of the beam. So this right hand side of the beam is providing these internal forces to the left hand side and keeping it, maintaining the vertical equilibrium of the forces. This particular force shown in purple here is called shear force. Now this is not that a force that you have applied. You have applied only the force which is here. So this is your applied force. But this V is generated inside. So this is internal forces. Okay? So internal forces. So this is one part gives to the other to come into equilibrium. So how did you know that? How do we know the amount of it, direction of it? It is again using equilibrium. We make a virtual cut and then we see what sort of forces I need, or the support system I need from the other part to keep this side under equilibrium. Now, of course, the left-hand side in return gives to the right-hand side exactly the same amount of force in the opposite direction using Newton's third law, equal and opposite. So, is this under equilibrium? Possibly not. Summation of vertical force is 0, but may not be the moment is 0. So, of course, the right-hand side also gives rise to a moment as well. So, this moment M is called bending moment. So, V is the shear force and M is the bending moment. Now, both of these, so this is not moment we are calling now, we are calling as bending moment. Both of these are internal forces. And then only this part of the beam will be under equilibrium. And of course, you could see that it will depend on where do we make the cut. If we make the cut towards very left, there would be one set of V and M. It could be very different if we make the cut at the mid span or a quarter span, or maybe 3/4 on the right hand side. So this would vary, the internal forces would vary if you go along the length of the beam. And when you draw that, when you plot that along the length of the beam, that becomes your bending moment and shear force diagram. So just to summarize, you cut off a piece of a beam and ask what stress resultants are required for equilibrium. So M is here a bending moment and V is a shear force. And as I said, M and V will normally vary along the beam. So if you did a cut here, you will get a different values of M and V. And just before I move on, to highlight, these V and M are internal forces or internal stress resultant. So they are not something that you are applying yourself. Your application of the load is only this bit at the top. Okay? What forces, stresses that are generated inside gives rise to this bending moment and shear force. And these are highly important because that is actually stressing the beam. And from these shear force and bending moment, we can find out or we can calculate what would be the stress. And once we know the stress, we can check with the material properties or the material behavior that this beam is made of and compare. If the stress due to bending and shear is less than the material strength, then the beam is fine. Beam can survive that load. If we find it is either equal, then of course this is at a balanced position. And if the stress is due to bending moment and shear force is higher than the material strength, that means beam has long failed. It cannot carry that much of load. So it's essential in design. So if you are given a set of load, given a span of beam, that's what you do. First find out what is the bending moment and shear force along the length of the beam. Pick up the maximum location, find the stresses, compare that with the material behavior. Okay, that's probably slightly further way down. We'll definitely revisit this bit, how to do design, but that's the context of it. Why do I need to know about these internal forces? Because those internal forces will give rise to stresses, and that's what we need to compare with our knowledge of the material property that the beam is made of. So shearing and bending. So shearing is normally, the name suggests, it's shear one part respect to another. So imagine one piece of beam sliding relative to the next, and that gives rise to this shearing behavior. Whereas the bending behavior is very much like, imagine a beam being curled up or bent down, for example.
So when we are putting the load, the beam will bend towards down. So basically the bending moment is actually countering this, the bending moment caused by the load. Is that
No, the sequence is that imagine you have got a flat beam onto support. You put a load onto that beam, and that load will go to the support. Means whatever you put, that's your whole purpose. Take the loads. Imagine this is a bridge. You are standing on the middle of the bridge. Your load must go to these two, either of these two ends, right? Now, as it moves, as the load, the way it moves to the end side, then what it does is it creates so-called bending stresses and the shear stress within the beam. So you can think of that the beam starts to bend to resist the load. So bending is an after effect due to that deflection. So you could have little deflection or small deflection, depends on the material. So if you have got a very soft material, it will bend more than the other. But nevertheless, even if it is a very rigid type of structure, beam, it doesn't bend much, but still there would be bending moment. Okay? So the deflection or the bend up profile is an after effect. Is that makes it clear?
the bending moment here is upwards. So is it countering the bending provided by the load?
Oh, that bit, we'll come to that. So hold on to that. Okay. So if that's a question, hold on to that. We'll come to that. What is opposing what? So that will be clear when we do the sign convention. Okay. So hold on to that. So shear failure could happen into a structures. For example, one side sliding over another could happen to a bolt, for example. So one side maybe having, so if you imagine this bolt is holding two plates, and then you have got a force from one side, and then it could be sheared off in the middle, for example. Bridge, for example, could be simplified as a beam, and then you could think of you putting a load on top of it, and then bending moment could be in this way as well. So that's a bending moment diagram. In the diving board, for example, bending of an aircraft wing, for example, so the lift on the underside of the wing would create bending of the wing as well. don't know what is this one is. I have no idea what that is. Let me try that. Let me try what it is, first of all. I don't know whether it will pick up the... Come on.
He was also there to watch.
Sorry.
Needed to know if the 777 wings could survive the strongest forces that turbulence or bad handling could produce. They were also interested in whether the same wing design could be used on future, heavier versions of the plane.
So this is a testing of a big wing.
It would be a simple question to answer. Just attach strong cables to the wings and pull upwards until they broke. As the test progressed, the force on the wings became so strong it caused ripples in the fuselage. The engineers hoped that the wing would withstand 150% of the strongest forces it would ever meet in flight. They predicted a wing deflection of about 24 feet before the break.
Retention, we're now holding at 120% design limit load. We'll again make a loads check. It should be a short hold here.
Just note the amount of bending that has taken place. Huge amount of bending. So when you are on an aircraft and you see the wings are flapping quite a lot, possibly nothing to worry about, because you could see that in the test that quite a high amount of deflections already has taken place.
As the tension in the wing increased, the crowd of observers, including many of the people who had lived with the plane for more than 4 years, fell quiet.
Condition 15 in 75 seconds, starting the ramp now. Retention, we're now loading to 130% of design limit load. The ramp rate is again 75 seconds.
Although he was no longer the leader of the team, Alan Mullally was also there to watch.
This image will give you a context of it. So this is the fuselage here, and you can see the amount of bending the wing has taken place. So still not failed.
152.
It's another view on the side.
153. 153. 154.
Whichever way you looked at it, the test was...
So the point is that a beam is a very good mechanism to resist load. Now, it carries huge, and if properly designed, it can sustain huge amount of deflections without failing. So the deflection is an after effect in that sense because of the bending. It not necessarily, yeah, go on.
In the video, they mentioned that they have pulled it to an extent of 150%. That is 50% above the design limit. So if it is designed for 100%, how it is able to withstand that?
No, it's some factor of safety that they put it in. All the structures come up with a factor of safety. So because we don't know the material constructions, so some amount of uncertainty is in there, all cases. Yeah.
Do we need to know why the wing
So do we know this excess load at which it will break? That's the question.
Because the excess load, I expected the wing to just break. Instead, it basically blew up.
Yeah, so that's a type of failure called brittle failure. You are right, good observation. It depends on the type of material you use. So these are probably some form of fiber composites, for example, so which have got the brittle failure mode than the ductile mode that you would be observing with a piece of steel, for example. Steel will bend usually before it finally snaps, whereas some material would fail as a brittle manner. Yeah.
So the explosion is due to the buildup of potential.
Build-up of the stresses, yeah. Okay, so I'll try to get some more other things as well. So again, if you think about it's a bridge that you are building, and this type of form of construction is called balanced cantilever construction. So what they do is they build the pylon or the column or the pier in the middle first, and from there they build on the two sides so that each side are balancing to the other. So this is called a balanced cantilever construction. And you could see in this case that if you consider the middle pier is sort of a support, then you have got a load due to the weight of the bridge deck and plus some plants in the end. So it will cause it to bend. So you'll have a shear force diagram as well as probably a bending moment diagram. So no need to know now, but we'll see what are those and how it is done later on. So more material is required near the support in this case. As you could see, in the case of the bridge deck, it has got higher depth near the support and relatively lower depth as it goes towards the end. So stresses due to bending or shear is higher in the case near the support. So that's why you put more material in terms of the thickness in here. So you have got more material in this side rather than as compared to that point over here. Again, say Burj Khalifa, for example, you can consider it's a cantilever structure, and due to wind loading, which would probably vary in a triangular fashion as you go from the ground to the top, and then that would create bending onto the structure. Now, consider what is the thickness or width of the structures near the base as opposed to the top. So you need more material in this part, of course for other reasons as well, vertical load as well, but even for sidewise load like wind, you need a higher area near the support, as same as you did for these cases of the bridge. Now these are all related to what is called bending moment diagram. So Burj Khalifa, for example, is about 828 meter high, and then let's say you have got wind pressure in this format, then from that you can find out how much stresses that would be generated in here. Okay, so that's the base of the formal presentation. What I'm going to do is, next I'm going to answer a few of your questions before I go on to describe you more about this bending moment and shear force diagram. So if I go to document, okay. So the questions some of you have asked me as follows. So the first question is, some of you have asked about tomorrow's test. What is the syllabus? So test tomorrow is 4 to 5 o'clock. Now, it won't be for whole 50 minutes. Mostly it will be at the most half an hour, okay? At the most half an hour test. So it will be online, as I said. So test would be online, and it would be different type of questions, multiple choice. So it would be multiple choice of questions, or you could have click something, click on an image, matching one side to the other, so matching answers, questions to answer, matching questions to answers, and write a short couple of lines. Write a short paragraph, for example, true or false. So multiple type of questions could be there, but mostly it would be within 30 minutes. And I don't think you have to struggle for the time, let's put it that way. So you should be able to finish 20 minutes maybe. So I'll give the questions that I can solve within 10 minutes. And as this is the first test, so I'll give you 3 times more time, okay? So you will have 30 minutes, okay? Yeah.
How many questions there are?
It doesn't matter really. It could be 20 or 2, it doesn't matter. So it will be mixture of the things. Bring in a calculator, some paper, and pen or pencil, whatever you use, and of course this should be open book and open computer and everything, so you can bring whatever your notes, anything, that's fine. What you are not allowed is talk to your next person, and you will be getting individualized paper. So paper may look the same, but it would be the values and the other things, choice of questions would be different. So if multiple choice 1A is for you, may not be 1A for you. The correct answer may be 1D or something for the next person. So this would be all different, and it would be all mixed up questions as well. So you may not get that in the same order, the questions. So you may get a question slightly one before, and all the questions would be all together. So for example, you need to make sure that you can move from one to the other one. Okay. So that's about the test. The syllabus is reaction forces and equilibrium. So syllabus is reaction forces and equilibrium. So no trusses, but I may give you a problem like this. I may give you a truss, and I can give a force like here, 2 forces, and I ask you to find the reaction forces. So I'll not ask you to find the member forces, but I may ask you find the reaction forces at the support. Okay? So the reaction forces and equilibrium you need to be able to solve. So it's not the member forces joint by joint you need to do, but you need to get the reaction forces. Yes?
Wait, so
I cannot hear you. So the question was, quiet please, quiet. So the question was whether we need to do stay with the free body diagram and we'll be able to get the answer. Yes, that will be the case. Okay, so that's about the syllabus. Any question about the test? Yeah. Yeah, writing a short paragraph could be, I could give you a problem and say, write down the steps to solve this problem. Louder. Your friends are speaking. Louder. Oh, significant figures. Okay, that's a good point. So normally if there is a numerical question, say the answer is say 25.3. Now normally you will have an accuracy of plus minus 1%. So put 1 to 2% depending on the question. So put in enough figure so that you are within plus minus 1 to 2%. Okay? So put in enough figures in there. Any other question on the test? Okay, about the devices. So I have asked to book one of the computer cluster in this floor. So hopefully I'll get it. If not, they haven't replied yet. If not, there are few computers outside and also the computer slightly down the corridor. So most likely I'll get the clusters down the corridor, computer cluster 3. So those of you who will not have a device, either a laptop or a tablet or equivalent, you could then go to one of those clusters over there, and then of course there will be somebody to invigilate you, and if you need any question to ask, they would be there. But the question is one thing to be aware of. It will be time test. So after, say if it is given 30 minutes, after 30 minutes, whatever stage you are, you will be logged out of the test. So whatever you have done, it will be saved at that point and submitted. So if you didn't submit by that time, don't worry. It will, if you have saved the questions by that point, then that will be saved and it would be submitted for you. So that timer will take from the point you start the begin button of the test. So if you need to read the instruction first, take your time, but when you click the begin button, then the test would start and you will have only 30 minutes from then on. So be careful with that and don't submit the submit button in between. If you do, then the problem is you have to restart again the test. And then if I have to manually restart you cannot do it. I have to restart it for you. Then you lose all your works. You'll get a new set of questions. Okay? So be careful with submitting button. Don't submit until you are fairly sure you have done everything. Don't press the submit button. If you do, then you may have to redo it again with a new set of questions, which is not pleasing. You may have said, okay, I've done it, and there is no other way I could put the both things. I have to either give you a new choice or take the old one. In terms of, some of you said, okay, so that is regarding the test. In terms of availability, some of you said that you will not be here tomorrow for one reason or another. Some email I have received, people are not well, for example. Now for that purposes, there is a mitigating circumstances form. So you need to fill in those mitigating circumstances form, and then the school mitigating circumstances committee will look at it and give you appropriate instruction what to do in those cases. So some of you are asking whether you could take it from home. No, you have to take it in the sort of semi-invigilated conditions that the rest of you will be taking tomorrow. So that's about it really regarding the test, and it is worth 10%. So in terms of the practice question, if you do tutorial 1, that's the type of problem that you will be looking at, and the type of problems that we did in the tutorials over 2 weeks back, last 2 weeks back. So it will be similar to that. So what you need to know, for example, if you have got structures like this, and if you have got a uniformly distributed load, how can you calculate the reaction force? If you have got a beam, and if you have got a triangular load like this, for example, how do you calculate the reaction force? That sort of problems. That sort of problems you will be getting. Or the moment of a force, for example. So it won't be difficult, but you need to know the method. Any other question? No? Any other question regarding the test? No? Okay, and in terms of the blackboard, what I have done is I have put in the solution for the truss tutorial, and there is a tutorial sheet for tomorrow. Of course, we will not be doing in the class, but that is for you to try, and then I will upload the solution later on for you to try. So there are 3 truss problems for you to try there, and then you need to do that, and then I'll upload the solution. Truss would be our next online test, which could be depending on when it is written in the coursework timetable. I think it's week 7 or something, isn't it? So then we'll have the next test on truss. Next test would be trusses, not the coming one tomorrow, the following one. I have to look at the timetable for the, let me look at that. Yeah, that's on week 7. Week 7, 2 weeks from now. Okay, so okay, imagine you have got a truss like this with supports in that way, and the truss is loaded at say twice F at that point. So how this load would be taken by different parts of this truss member. Now this is a truss, not a beam, so each point is hinged. Okay, so to analyze this truss, this is symmetric as you could see. So there would be reaction force F in there and reaction force F in there. Now what about the forces in the members? Now we can find that out by using a method of sections. So if we say, okay, I take a section at this point, then of course the member force here would be F times, so if I take moment about this point, for example, so I have got three unknown forces, this one, that one, and this one. Now, if these angles are 45 degrees, I mean this distance is equal to the top one, what do you think the forces would be from the top and the bottom? So if I take moment about this point, then this force times that distance would be same as this F times this. So what would be this force, you think? Would be? Minus F. So this force is minus F. What about this force? So if you take for a moment about this point over there, then it is going to be cancelled by these two. So you will have F times 2 is balanced by this times half of the distance. So that means it would be twice F, right? Approximately. So this is approximately twice F about this distance. So if I write it down, so this is minus F. So this is compression, and this is slightly higher force, let's say 2F, with a tension positive. What about these two members? Again, if you take moment, if you take a cut at this point, you will have forces in this direction. So if you take moment about this point, that is F times twice the distance, must be balanced by this force times twice the distance. So that would be minus twice F. And then similarly, if you take about this point, then that is F times 3 divided by this distance over 2. So you'll get this is a plus 3F. So if you do this one, you'll get this is at the minus twice F, and then that is a plus 3F. The same things repeat on the other side as well. So other side, if you do the calculations, then you'll get this is compression, and that should be tension, and then there will be some in here. So the same situations repeats on the right hand side as well. So you would probably get compression there and tension there. So a truss loaded by a vertical load in the middle will have the top bars will be under. So two things you could see. So the some observations you can make from here is the top bars, or chords sometimes are called. So top chords are in compression. So top chords are in compression, that you could see. Second thing, the bottom chords are in tension. Bottom chords are in tension. And also third thing is there is a pattern. There is a pattern to the amount of force. To the overall tension and compression. And what is that pattern? So the pattern is as you move towards the center, the absolute value is increasing. So if you move towards the center, then the magnitude of tension or compression increases. Magnitude of tension or compression increases. And this is exactly what happens if you have a beam. Now imagine you have got a beam which is that big. So if I substitute that by a beam like this, and the beam is supported here and by a load in the middle as twice F. Now of course the reaction force here would be F and F. Then the top chord will be under compression. So the top fiber is under compression. And the bottom fiber is under tension. Now also in this case it will happen that if you come towards the middle, this compression would increase and so would the tension would increase. So as you come towards the middle, this compression and tension amount will increase. Exactly the similar pattern as you can find in a truss member. So this is caused what is called by bending moment. And how you draw that? We imagine this is the beam line. So imagine this is the central line of the beam, and that you are plotting it here, and you will plot the amount of tension and compressions as you go. Say for example, if you take it here, that the compression and tension would give you a moment, and if you say okay, I am plotting that moment at that location, that's the bending moment at that particular location. So if you draw that, that is what you give you something called a bending moment diagram. So that is what is called a bending moment diagram. That means at this point you have got a compression, and this point you have got a tension. That creates that moment. And as you could see it here, that moment will increase if you go towards the center. Okay, I will discuss it next week, much more detail. Okay?
When I was doing this particular, to find the horizontal forces, we just used the equation to make them in equilibrium, but we couldn't solve because both of them are unknown. So then we have to take the moment about.
So you just consider one side.
I also wanted to ask, why is that the case?
Because you know the moment is zero at that point.
Okay.
So if you say okay, there is a reaction forces at that point, horizontal and vertical, that would be opposite to the other side.
Okay.
And then you can find out this is like a simply supported case in that case.
And I also wanted to ask, if we know the distance from here to here, how do we know if this is clockwise or anti-clockwise?
So the way to imagine is, if you're taking moment about this point,
Perfect.
so you are thinking about that force, which direction it is your member, so which direction you think this is going to rotate?
So the same as this one. Okay.
So imagine this is the member.
It always depends on where you take your moment from.
Absolutely. Rotation about that point, whether that's a clockwise or
So I
anti-clockwise.
should think of it as showing a member and then I go about it.
That's right.
Oh, yeah, go ahead.
So is like the bending moment same as the moment that is exerted?
Bending moment is internal.
It's the opposite direction.
So bending moment is slightly different. Bending moment is what is developed inside.
I didn't understand.
So the moment is, this is the moment of the force, not bending moment.
So, but what's the direction of the bending?
Bending moment in this case, you have to analyze that first of all, find out the reaction forces, then only you'll get the bending moment in here. Bending moment is the internal force. You need to make a cut there and then see. Moment is different than bending moment.
Thank you, sir.
Okay. It's a bit confusing, yeah.
For the earlier example, how do you get negative F? Actually, I don't really understand from this part of it.
So if I take a force like this, okay?
Yeah,
So this sort of, if I take a moment, so there are three forces that is possible, right?
correct.
So if I take moment about this point, these two forces, moment is 0.
Yeah, correct.
So only that has to act in that direction to compensate the moment due to this.
Yes,
So that means this is compression.
correct.
So if this is compression, also if you think about taking moment about this point, moment due to this and this would be cancelled.
Yes,
So this is going to create a clockwise moment that
Correct.
must be created by an anti-clockwise moment. So that would be a tension.
Can you repeat it again?
Yeah. So if you take moment, so there are four forces here, right? This, and this. So 1, 2, 3, and 4. So if you take